Thanks for joining. My name is Akram Al-Hourani. I'm an associate professor at RMIT University. First, I would like to acknowledge all the collaborators. I didn't have sufficient space to list them all here, but this work wouldn't be successful without them. At the beginning, I would like to give a quick background on the current satellite services and how they evolved towards the mega or massive satellite networks. And then I would like to enlist the challenges or some of the challenges related to these mega massive networks and how artificial intelligence can help us in resolving some of these challenges. Thanks again for the introduction. About 4 billion people are still outside the internet connection, which is absolutely true. So if you look at the figures from the United Nations, you'll find a stark difference between developed countries or offer around 90% connectivity versus developing countries, which are still around 50% of connection. Now, if you look at the least developed countries, you'll find the connectivity is only 20%. And if you zoom in further, you will find this figure shows the connectivity comparing rural areas versus urban areas. So if you find in some places in Africa, for example, the rural connectivity is not exceeding 15%, while in urbanized areas, obviously you'll have much higher connectivity. And here comes the opportunity of satellites and low Earth orbit, new generation of low Earth orbit constellations in bridging this gap and providing a connectivity for the remaining public population. A quick review on the classes of service that are being traditionally offered. So we have the traditional system, which is called the fixed satellite services. These are from 40 years till today, these were the dominant type of service. So basically you have a large coverage area where you have a transmitter sends to the satellite. The satellite is an analog repeater. It takes the signal and transmits it back to the entire region. Obviously, the drawback here is the spectral efficiency, because if you're transmitting something, the whole continent is being, the spectrum on a whole continent is being occupied. To resolve this, the high throughput satellite services, or HTS, applies the concept of multi-beam, similar to cellular system, where you can reuse the frequency resources and thus provide much higher bandwidth and throughput. Also, we need to cover the traditional land mobile satellites. So these are designed for high mobility. Also, traditionally, it could be provided either from a geostationary orbit, obviously not globally, but for particular regions, or can be provided through a low Earth orbit. Typically, these are not as high throughput as the next generation that we can look at. I also need to cover the IoT-over-Satellite. So the new class of service that is non-human kind of machine-related traffic, which includes things like utility metering, logistics, and so on. Now, finally, the new generation, which is the mega or dense or massive. I think there's no yet consensus or what to call them, but they are basically in the low Earth orbit. And the idea here is to move towards an integrated service that provide both broadband services to users, whether they are in urban environments or rural environments, also to provide IoT connectivity. So what are these mega satellite networks? Now, this is a simple simulation for a constellation called Walker star. And we can see here the idea of having this massive amount because you're using a low Earth orbit. Your coverage extent is not large. You need to cover it with many satellites. The other thing is also you want to reuse the spectral resources similar to cellular networks. So you need a lot of base stations or a lot of satellites in this case. There are a lot of opportunities, of course, as being also introduced previously. These potentially can provide lower latency than even current optical fiber terrestrial networks if you can route the traffic through the satellites. And here's a simple simulation. Current networks don't work like this, but in the future, if inter-satellite connectivity is enabled in a working correctly or working in its full capacity, you can route traffic. Here's an example between Europe and Australia, and we are connected through entirely through the satellite. Now, to give you an idea, at the moment, most of the networks, the satellite will relay back the traffic to the nearest ground station, and from that ground station, the traffic will be routed through the international optical fiber networks, which means through the internet. These are two examples. So I extracted these PLA elements from yesterday. So you can see this is OneWeb on the left. It's a constellation. I say this is a Walker star constellation, and there were 636 satellites. And you can look at SpaceX, it's 4,200 satellites as per yesterday. This is a massive amount of satellite. Even my computer crashed yesterday when I was trying to record the video. Let's look at the challenges with this increased number of satellites and how AI can help us in resolving some of these challenges. So first and foremost is the spectrum. Now, spectrum is a finite resource, radio spectrum. C-band, for example, which is almost totally occupied. Ku band and Ka band are now nearing depletion. So operators are looking into higher spectral bands like the QV band. There are big problems of using this, whereas the opportunity is that you have a huge bandwidth, but the problem is they are heavily affected by the rain attenuation. So we see how AI can help us in this manner. We have a huge challenge in integrating satellite network with terrestrial networks, because you don't want to hold two mobile phones, obviously. You want to move seamlessly between terrestrial, for example, in an urban area, into a satellite covered area, for example, on a highway or in a rural area. So we have performance modeling of these hybrid networks, and large constellation is a very nice and open area of research. We have also the constellation design. This is also higher layers, let's say layer 3, and how to connect in the network topology, how to provide these inter-satellite networks, as well as been mentioned, Dr. Yani mentioned the opportunity of new hardware to be developed, such as optical links or terahertz connectivity between satellites. And then eventually we have this security of these networks, because satellites are up there in the space and their coverage is wide, very wide, and by nature it's broadcast. That means you need to provide some intrinsic security in satellite. So let's look at the AI. Well, look, I try to shorten this slides as much as possible to fit with the time. So I'm going to talk here about a project that we've recently completed with alongside OneWeb. It was a collaboration, very interesting collaboration. So what I'm showing here on the right side, the x-axis is the time. The y-axis is the excess path loss. So this is the additional path loss between a ground station and a satellite operating at the Q-band. So you can see at some events here of heavy rain events, your attenuation is exceeding 15 decibel, which makes such frequencies very hard to use. So there's a huge severity in the attenuation. So what the AI can offer here is to predict such events of heavy attenuation. And you can tell the modem, for example, here's another simulation. You have a ground station here. You have multiple satellites you are connected to. So one option, you can switch to another satellite, or you can switch to another frequency band entirely when the fading is expected to increase a very high level. So that project delivered with collaboration with OneWeb and supported by Australian Space Agency. And so there were two components of it. One component is to model the QV band for low Earth orbit, and the other component was to provide prediction for future modems and future units. So they can do either change the modulation scheme or change the satellite or change the frequency band. If you're interested more into this work, you can refer to the publication recently was accepted in the IEEE transaction on machine learning in communication networking. The second thing I want to talk about is the radio spectrum. So to understand the problem of interference in satellite, probably the nearest thing we can get at the moment was a drone. So in this experiment, we have this UAV fitted with a software-defined radio and a mini onboard computer. So what we did is we flown this UAV at different altitudes. So you can see these three figures represent different altitude, 18 meters, 60 meters, and 100 meters. The x-axis here shows the frequency. This is the ISM band, or part of the ISM band in Australia. And the y-axis is the recording time. So near to the ground, the drone was able to capture a few of the transmissions. So this is, again, this coming from electricity meters. But as we increase the altitude of the UAV, you can find that you can see that the interference becoming much and much severe. that means from a satellite perspective, you will find millions of these transmissions. You might find you will not find any spectral opportunity to use the spectrum at such a very high altitude as the satellite. So one way as well, because this talk is about AI, is AI is a big umbrella of so many things, including unsupervised machine learning. So in this work, what we're showing here, the left-hand side is the recorded spectrogram. And the idea is a satellite or a receiver can find spectral opportunities. The white area here is a spectral opportunity that can be used in an opportunistic way. So the idea is here to use machine learning, so you can identify the spectral holes in more efficient way and more confident that you can use these locations of the spectrogram. If you're interested in this work, there's another paper in this regard published in the Internet of Things journal. There's a current project we are working on. It's a very large project, involves multiple universities and international collaborators. And the idea is to borrow concepts of cognitive radio. Now, people in the communication, they know the cognitive radio being investigated for the last probably 30 years. And the idea is to borrow some of this concept and try to apply it into satellite LEO Earth orbits. And that's to mitigate interference and also to enable the adaptive sharing, collaborative sharing of the spectrum, either in an opportunistic way or in an autonomous way. Because don't forget, when you have, for example, OneWeb and then SpaceX, and then you will have multiple networks coming, you need to find some autonomous mechanism to allow this spectrum to be shared and to maximize the efficiency. You don't want this constellation to interfere to each other and eventually degrade their performance. So let's look at also what's the role of AI for satellite communication. And in this particular, there's a lot of work being done, very nice work from researchers around the world on how to use deep learning for recognizing packets or recognizing telecommunication frames, wireless frames. So the idea is to use deep learning here to decode or to demodulate, in this example, in this paper, to demodulate chirp-based modulation. And someone would come with this idea, so AI is not the best solution for everything. There's a big hype around AI these days. AI can solve for you some sort of problems. For example, we found that AI is good when you have interference, but then you can just use traditional methods such as matched filtering when you have thermal noise. And for example, matched filtering is proven mathematically that this is the optimal way of detecting a signal. So what this paper was about is to find a kind of a balance, a switch. So you switch between a traditional detection when you have a noise limited system versus you switch to a deep learning detector when you have interference limited system. So in this manner, you marry the best from the traditional classical systems and the AI system. And if you're interested, this paper also been recently published and it is available on IEEE Explore. People worked in machine learning knows that the process of teaching a machine or even doing prediction is resource intensive. Resource intensive, you need a high processing power, and this high processing power consumes a lot of energy. So if you want to implement on board of a satellite some AI system, there's a lot of power consumption that the satellite might struggle to provide the processor. And at the moment, all our computers, what you're using now, whether a computer or a tablet or a phone, is based on digital architecture, silicon-based digital architecture. So the idea is there are some networks which are inspired by human brain, neuromorphic networks that are expected to have much lower energy consumption than the traditional AI, like the CNN network. So this is called the spiking neural network. And what we show here, that spiking neural network can still be used for detecting and mitigating interference in satellite applications. So this paper is still under review, but we have it on archive if people are interested to have a look at it. The last topic I would like to cover is the performance modeling in the LEO satellite or the mega LEO satellite. Now, traditionally, again, we have one satellite, bent pipe architecture. People are expert in link budget analysis and transponder design and so on. But when it comes to a vast number of thousands of satellites, and probably interfering to each other, interfering to other satellites, it's very important to start looking at some analytic tools. Analytic like mathematical tools that can capture the essence of that performance and link the design parameters with the desired performance metrics. Now, of course, you can run simulation for that, but simulation is usually a time-consuming exercise and does not usually provide you a clear link or a tractable link between the input and the output. So what we've done here and also there's very good teams around the world working on a similar problem. There are tools from mathematical tool from stochastic geometry where you can use for providing some nice analytic expectation on the performance. So here is an example of three models. So one model is the polar, the Walker star, for example, OneWeb. We have the Walker Delta, which is Starlink. And then what we came up with, which we are using, is the random model. We randomized the orbits. Now, this is not highly practical, but what we found that it really doesn't matter at some point when you have thousands of satellites, it really doesn't matter how they move in their orbit. The performance of such networks started to converge. And I'm not going to cover this in much depth here, but you can, from this graph, for example, one of the performance metrics, which is under certain conditions, the design conditions, if you vary the number of satellites and you trace the performance of the analytic or random constellation, the one we proposed, versus the practical constellations such as Walker Delta and Walker Star, you'll find that, first of all, your performance is quite close. And second, the performance of the analytic system is the bound of the practical systems. The difference is in the analytic system, you will have very nice equations and easy to evaluate. And will give you a relation between the input parameters and the desired performance metric. In this example, the desired performance metric is the coverage probability. This is another exploitation or another application of this analytic model. So in this paper, this work, we're trying to optimize the altitude for providing the best coverage. So what you can see here in the x-axis as an example is the constellation altitude in kilometers. The y-axis is the probability of coverage. And you have different curves representing the different numbers of satellites in a constellation. Now, all these equation lines are obtained using analytic. They're verified using simulation. But the idea is these equations can provide you close to reality of the performance and provide you insight on the analysis. So this is another example on optimizing the altitude. In the left side, you'll find a network with a higher altitude of about 1,000 kilometers. The right side network is provided at 400 kilometers, and you can see there's a vast number difference in the amount of satellites. So from one end, more satellites is better redundancy, but also more interference. So there is a balance here where to provide an optimal altitude. There's another work trying to optimize the beam width. So if you look at the spot of the satellite, the spot is now increasing, and now you have kind of full coverage. You close the coverage gap, but as you keep increasing the beam width, satellites will start interfering to each other. So again, there is also an optimal kind of a beam width where you balance the interference and the coverage. Now, just also to let you know, practical satellites would not have a single beam. Practical LEO satellites would have multiple beam. But that's an approximation to show you that there is an optimization here that can be done. Another aspect that in the modeling is the duration of the satellite path. Now, this hasn't been, I mean, usually you run a simulator will tell you when the satellite will arise and when it will fall. But using mathematical tools will help you even to simplify this problem. For example, one of the work that we have done is we came up with a much simpler solution for a randomized constellation, which shows you a very simple relation between the altitude of the satellite in kilometers here and the average availability time in minutes. So if you take an example of a satellite at 400 kilometers, you can calculate the average availability minutes For example, at 1,000 kilometers, you will get around 13 minutes of average availability. So this equation very handy if you want to do quick calculations for your constellation, and then you can employ, for example, simulation to do detailed analysis. Okay, so I will cover a takeaway. I still have a couple of minutes. So the main takeaway, so why I did cover this modeling, because if you want to run AI to do for you optimization, or to do for you even modeling of the performance, you need to have some equations so to feed this AI machine. We are not yet into that stage, but what we're trying to do is to develop the models, the equations that can help you later to run an AI to do the optimization. So again, so as a summary, AI can help you in so many different aspects. So here's a paper still under review. It's available. There is detailing what's the role of artificial intelligence for the networks, for the communication aspect in next satellite next generation satellite constellation. First, it will help you to do radio forecasting. We saw a detailed example on that, an actual project done, spectral sensing and classification of the occupancy and classification of the different packets being received. It will help you to optimize the topology of the satellite. And then here we're not talking about just single shell. You might have multiple shell, multiple layers of this constellation. It will help you to optimize the access network and to balance the resources between the terrestrial spectral resources and satellite spectral resources. We also covered the stochastic geometry has a very good role here to play in providing the needed model, whether you want to use them as standalone or using in conjunction with the AI. We also looked at AI signal demodulation, whether it's just the demodulation part. We haven't looked at the end-to-end communication, but this is also an excellent area of research. There are a lot of work being done. Not yet applied on satellite, but this is a very interesting area. There are new hardware types. I haven't covered that, but that would be also very interesting because we needed networks such as the SNN network, the spiking neural network, which has much lower energy consumption than traditional CNN networks. All right, so that was supposed to be the end, but if I still have a couple of minutes, I want to cover this interesting work on using machine learning for security, for physical layer security. Now, spoofing is a very big problem in satellite communication, and the idea here is to use AI or neural networks to identify hidden features in your hardware. As such, if someone pretended to be you and pretended to be a satellite, for example, the other unit can detect that based on hidden features in the RF chain. Okay, so that's it from my side. Thank you very much for listening. Happy to take questions.
Thank you very much, Akram, for this very interesting presentation.